My name is Arild Burud. I'm working in the IT department at Met Norway. My main responsibilities there are data distribution services, data importing services, uh, EU or European projects like Copernicus, where I'm participating in the Copernicus Marine Service and the Climate Change Service, and also EUMETSAT, OCSAF, among other tasks. Shuffling data is the main, is what I'm doing the most of the time, and making data available. And THREDDS now is the best tool we have to make data available for users around the world, internal and external. I gave a similar presentation last year in the WeDeal 2021, but I'll have some additions to that as well. There are a few acronyms that will show up during this presentation, and you will be free to look them up later on. But the main part here is netCDF and THREDDS data server and OPeNDAP, and also a number of conventions and standards that we're using in netCDF. Before netCDF arrived, we exchanged data and we made data using a variety of binary formats that were not easily accessible for the rest of the world. Everyone was using their own native formats for storing and archiving, and it was not very easy to distribute data when you needed to have a separate program or a lookup table or documentation to know what you were actually getting. netCDF was trying to solve this problem by making a format that was self-descriptive. As I said, as it says here, the project started in 1988, has developed over the years and is still developing. Just 3 years ago, they added Amazon S3 objects support, and last year they actually also added support for the ZAR format. So, but still keeping netCDF as the top level format or protocol, if you like. It's a format that can be expanded in the future and still be backward compatible, which is one of the main benefits as I see it from using netCDF. The basic components of netCDF file is to store data, store information. It could be an array of data, it could be matrices of data, it could be matrices in several dimensions. It could be like this simple illustration is showing, could be that you have just a grid or a matrix of values that are evolving over time. So you actually stack the time representations in a matrix of 3 dimensions. It could be that you can add multiple dimensions, as we have done over the last years. You could add atmospheric height or ocean depth as a dimension, or you could even work on ensemble models, as we are used to see for the past 10 years in atmospheric models, that we are an ensemble number as a dimension as well. This is expandable, but the main point is the format is self-describing. When you're looking at precipitation, you may have a variable called rainfall, but the netCDF file allows you to supply attributes like the units here is millimeter per year, or you have a method to say anything missing value is represented by a specific number. You can also add attributes that will tell you something about the form of data. Is this a mean value over a certain amount of time, or is there other attributes that you can use to further describe what you're actually getting out of the data? And you also have what we call global attributes in netCDF. These are the attributes that tell you something about the file and the history of the file. Conventions that are used to explain the metadata. So you have actually metadata about metadata even. This adds to make each individual file self-describing. It means you can copy this file to an external location. You can have people reading the file, and they will understand what the file is containing. And it will also, as long as you adhere to the standards, it will also allow programs and software to access these files in a consistent way. For instance, as long as you supply SI compatible units, you can have software that converts these units. So you can mix files that have the temperature in Celsius and temperature in Fahrenheit or Kelvin, and you can have the software actually convert this on the fly. You can have the geographical description, like where is the grid located in space, and you will have visualization tools that will allow you to put the values on the map in whatever projection you like. So this is where the netCDF format is actually competing or is becoming successful. So it's all about portability. It's about being able to know where data comes from and why it's there and how it was made. To be able to utilize all this metadata, you need to follow conventions. We recommend the CF convention, of course, which is like the fairly basic standard. There are also more standards like ACDD and COARDS, etc. And these conventions regulate how you are naming the attributes and how you are filling the attributes with content so that you ensure compatibility. This is very important for traceability of the data. At Met Norway, our data comes from a multitude of sources. We are receiving data from national partners, international partners, much from the Nordic countries, but also from several European partners. And we are exposing or redistributing these data for on behalf of them in projects like Copernicus. We are also having a huge Lustre storage system that will allow us to store these data and then use our THREDDS service to expose them to the community. I'm not going to talk about NCML, but I'll just briefly mention it here in case someone is interested in asking about that later. We can present the data as, like Abdel Kader did in his presentation, as individual files, but we're also able to use THREDDS to aggregate data sets, which means that we are collecting individual files, typically along the time axis, and making a virtual data set, a virtual file that collects separate time series into a continuous time series if the data is compatible in this respect. I have an example that I'm going to use in this presentation, which is a ocean model, 2.5 kilometer model that we are running at Met Norway. And it has these properties that we can actually concatenate or make an aggregation of individual files for a continuous time series. As I said, we are using threads to expose data, netCDF data. It could be anything from observations, even single observation stations of single geographical points, or that we expose time series for. It could be satellite observations, or in what we call L2, L3, and L4 versions. It could be model runs of atmospheric models, ocean models, and wave models, etc. And the list is continuing. So, and this was actually commented on in the presentation as well, in the last presentation. Yes, we have a lot of data on THREDDS Metno, and it's really due for a refabrication of the catalogs. But if we look at something like the ocean and ice catalog, we, as I said, I will be using the Barents 2.5 kilometer model as an example. We can just select this data set from the catalog, and you will see that we have the we have two entry points here. One is to look at the single files directory or the aggregation. If you look at the files, you will get a display of the individual files. Clicking on one of them, just like Abdelkader did with the WeMill files, is giving you this web page, which is showing you an OPeNDAP link, not to be confused with the OPeNDAP URL, because I'll be coming to that later on. But you can also download the file as a raw file with the HTTP server link, and you have the VMS and web coverage service links, and Godiva. Good demonstration of Godiva from Abdelkader, by the way. So I'll just skip this part of the presentation because you did a good job there. One comment. The Godiva 2 visualization tool is relying on external background maps. That's why when you use the default map, I noticed today the external background map is unavailable. It's on another server from another institute. So that doesn't show up, but it does show up on the Northern Polar Stereographic Views, because that's a different source. You'll have to excuse me, I have a sore throat today. If you look at aggregations, you will see one difference between aggregations and single files. That is that the file download is missing, because this is a virtual collection of files. It's not possible to download it as an individual file, because it's a collection of files. If you look at the OPeNDAP link, you will be presented with a page like this, where the important point is the data URL, because this is the URL you will give to OPeNDAP software. So it's not the web page, but the data URL you're giving to OPeNDAP software. This web page is actually giving you an entry into the OPeNDAP protocol, and it's not very user-friendly. It will give you a brief overview of the content of the data set, like global attributes, which variables are present, etc. But it's very not user-friendly for downloading data. We recommend you to use the OPeNDAP URL to actually download, because if I'm going to use this as an example, if you're going to extract a tiny amount of data, like a subset in time and space, from THREDDS or THREDDS data set. And in this example, I have chosen, there's a tiny white speck in the middle of the Atlantic called Jan Mayen. It's an island. And if you're a researcher and you wonder what's going on around this tiny little speck in the middle of the ocean, you don't want to download a 3 gigabyte huge file just to investigate what's happening around this little speck. You would say, I want a little rectangle around this island, and I only want the data around it. You would then use an OPeNDAP-enabled tool, and we at Met recommend using Phemex because we developed it ourselves. But it could be any kind of OPeNDAP tool, really. And you would say, okay, this little speck, I know the latitude and longitude of the area around it. I don't want to calculate the indexes that I need through the OPeNDAP web page, because that's very difficult to calculate the indexes. I want to use real natural coordinates, latitude and longitude in degrees, and I would use a program like Phemex, where I supply the OPeNDAP URL. I say this is a netCDF file. I want it to be, I want an extract in netCDF4 format. I want the temperature variable, and I want something between 69 and 72 degrees north and -7 and -10 degrees west. And I want somewhere between 20 and 30 meters depth from this model, and the time June 16th from midnight to midnight. And when I issue a command like this, I get a tiny extraction of the data set, and it's a 1 megabyte file of a 3 gigabyte original file, which makes bandwidth easy and easy to work on this tiny data set. The Phemex tool, like other tools, will extract only what you actually need. When you ask for temperature, you get the latitude and longitudes and the depth dimensions together with time. So you get something that's self-contained extraction. You can visualize it with a tool like NCView, and you will have this island more visible within this tiny extracted frame of the data. And it's much easier to work on. So what are the benefits then of using netCDF and THREDDS? THREDDS gives you the OPeNDAP URL. You can use that to extract data with natural coordinates. You can expose your data without thinking so much about directories or FTP servers or moving data around. You can recategorize your data regardless of how it's stored locally on your file server, and you can expose what you want to expose for the entire world. You can use these extraction methods that are available through OPeNDAP to extract what you need from a huge data set. And the THREDDS software makes your data available everywhere. So you have portability, and you have what fulfills an open data policy. And you have tools that can be used to regrid or interpolate or manipulate the original data further on. And this is actually used in our, sorry, Met Norway is actually using THREDDS and OPeNDAP extensively in our own production chains, so that we have the methods to extract what we need for further downstream productions. And we can merge data from different sources, global data with local data, regional models, etc., etc. Are there other solutions than Phoenix? Oh yes, of course, because the list of tools is growing. netCDF and OPeNDAP has become mature protocols, and you will find a lot of tools that will enable you to do what you want in your own favorite environment, whether it's the operating system or the programming language you want to work in. Most certainly there is a toolbox or a tool available for you there that allows you to work on OPeNDAP. Abdulkader mentions I should say more about OPeNDAP. I think I will limit myself to say that OPeNDAP is a protocol. You don't want to program directly on the OPeNDAP protocol. You will rely on a higher level tool that has enabled OPeNDAP and allows you to use OPeNDAP for data extractions, because the protocol itself is quite technical and quite heavy to use. When I look at what happens behind the scenes on THREDDS, I can see that one OPeNDAP URL is actually producing a lot of traffic because the tools are using the protocol extensively to communicate with the server. So what looks like one request becomes a multitude of requests depending on the tool and how they are utilizing the OPeNDAP protocol. So what about a look behind the scenes on THREDDS Metno? I could have made a graph here with a lot of boxes and connections, but I think I will contain myself to say, okay, we have a lot of traffic on THREDDS Metno. So what we ended up with was to have a redundant setup. We have two data rooms at Met, two separate data halls with separate separate hardware. So we have sorry, we have a load balancer behind the URL THREDDS Metno. There's a load balancer in each data room that will handle the 22 THREDDS servers behind THREDDS Metno. This allows us to direct traffic and to control the servers in a resilient and redundant way, and enables us to handle hardware situations smoothless, very smooth for the users. As an example, we had a hardware failure 2 days ago, and some equipment was down for 6 hours. No one actually noticed this on THREDDS Metno because we had enough servers that were answering, and traffic was just routed through the ones that were answering. So this gives us high redundancy, easy failover, and high throughput. And we have GitLab with continuous integration, continuous development. We have Docker images, and etc. We're also planning to introduce Kubernetes in the full setup of THREDDS Metno. Currently, it's only used on the load balancers, but we will considering to use this on the THREDDS machines behind the load balancers as well. Some key figures from THREDDS Metno is the total output in April was almost 470 terabytes. The daily output, the daily download from THREDDS Metno is about between 10 and 20 terabytes, at least 1,000 users per day, if you count IP addresses, 5 to 10 million requests, or 5 to 10 million asking for data. About 70% of the output is opened up, about 30% is just raw file downloading, and what we are exposing is a selected part of approximately 10 petabytes of data from the shared Lustre file storage system that we have. We have also helped WeMill in supplying a Docker image with a minimum configuration, and my colleague Trond Mikkelsen assisted in spinning up this for WeMill. It was a relatively simple task as we got the hardware or virtual hardware running, and it was very easy then to just expose a directory for WeMill on the THREDDS image using Docker, just mapping a local directory into a local directory in the Docker image. And I'm hoping this is actually going to work well for the WeMill project. A summary, quick, as my presentation is reaching the end. Create your data files as netCDF, add conventions and standards to describe the content, make it easy to read, make it transportable, make it traceable, and you will live a easier life. Expose those files through THREDDS data server. You can make aggregations, collections of data, you get a built-in viewer, you get OPeNDAP access to make it easier to users to extract what they want and only what they will need. And you get even the VMS service out of the box. Users are happy, the producers are happy, and people spend less time shuffling data around or answering questions on how to access data. And that's our happy conclusion on using THREDDS as a service at Met Norway.